Welcome to the deep dive. For years now, the story of large language models has really been defined by just one simple metric scale.
Right. Bigger models, more data, more parameters.
And we all know that path is getting incredibly expensive and, frankly, pretty cumbersome.
That scaling marathon, focusing just on size and data volume, it really defined the first decade of LLMs. But the research we're diving into today, it fundamentally changes the game.
How so?
It introduces what we can call a critical third pathway for advancement. And this path, it relies entirely on architectural innovation for parameter efficiency
And that's achieved how?
through the systematic recursive application of shared internal parameters.
And this innovation is all crystallized in Ouro, a family of pre-trained looped language models, or LoopLMs. Our mission today is to unpack the core findings on Ouro and really understand how these models are achieving superior performance, outperforming much larger standard models by fundamentally rewriting the whole process of reasoning itself.
It's a shortcut to being well-informed about where efficient AI is headed.
So let's start with the name, Ouro. It's short for Ouroboros, right? The ancient symbol of a snake eating its own tail.
It hints at the recursion, yeah. The central idea is that this architecture integrates genuine reasoning directly into the pre-training phase. It moves away from those explicit text-based steps.
So the thinking is all happening as iterative computation in the latent space. This is very different from chain of thought, which usually generates explicit text-based reasoning after the initial thought.
Right. The mechanism is a masterpiece of efficiency. A LoopLM operates by recursively applying shared parameters.
What does that mean in practice?
So think of it this way. Instead of having, say, 100 different layers all performing 100 unique operations, you have a small group of maybe 4 weight-tied layers.
And you just reuse them.
You reuse those 4 layers multiple times during the forward pass.
So you're using the same body of knowledge, the same physical size, but you're giving it the ability to think deeper by iterating on the input.
That's the core of it. This decouples the computational depth, how many thinking steps the model takes from the parameter count.
The model's actual physical size.
You get the brain power of a much deeper network without the corresponding massive parameter bloat.
That sounds great in theory, but training any kind of recurrent system is notoriously difficult. If you just tell a model to loop, won't it just get stuck? Or maybe just default to the maximum number of steps every single time?
That's the real engineering breakthrough here. They had to introduce a pretty sophisticated training regime to manage this internal dynamic. It's a kind of triad of training control.
Okay.
So first, you have the core iterative computation in that latent space. But then the crucial second and third parts deal with stability and efficiency.
What's the second component?
It's an adaptive computation mechanism. It uses a learned internal early exit gate that teaches the model to dynamically decide how many loops are needed for a given input.
And the third?
The third is a mechanism to prevent what they call structural collapse, basically, to stop the model from defaulting to the deepest step every time, which would just waste compute. For that, they used an entropy-regularized objective to ensure the model actually explored and used all the shallower steps during training.
So they had to build in these mechanisms just to force efficiency during training. And of course, even these officially designed models still require astronomical amounts of data. Ouro was pre-trained on 7.7 trillion tokens.
That is a truly massive investment, yes.
Okay, so let's move from the cost to the complexity to the payoff. When you put all this together, the recursive architecture, the sophisticated training, the huge data, what's the headline claim on efficiency?
The headline is crystal clear. Validated 2 to 3 times parameter efficiency gains.
2 to 3 times.
Yeah. The 1.4 billion and 2.6 billion parameter LoopLMs, they matched or even exceeded the performance of standard, much larger transformers.
Up to what size?
Up to 4 billion and 8 billion parameters, respectively, across a whole range of diverse benchmarks.
Hold on, a 2-3x efficiency gain sounds revolutionary, but we are talking about adding huge complexity to the training pipeline, plus using 7.7 trillion tokens of data. Is that gain really substantial enough to offset the complexity and data cost?
The results suggest the investment pays off specifically on reasoning tasks. The recurrent architecture demonstrates a very specific and powerful inductive bias toward multi-step logic.
Okay, give me an example.
For instance, look at quantitative reasoning. The Ouro 1.4b model, the one using 4 recurrent steps, it didn't just compete with 4 billion parameter models, it decisively beat them on tasks needing intricate calculations.
On what kind of tasks?
On GSM-8K, which is a math task, Ouro 1.4b scored 78.92. The Qwen 3.4b baseline scored 72.86.
That's a huge margin in a very challenging domain. You're seeing superior performance in the very area, that complex multi-step logic where traditional dense models often hit a wall.
That's it. And the larger Ouro 2.6b model surpassed 8b dense models on even harder tasks. It achieved 90.85 on the Match 500 benchmark.
And this pattern was consistent.
Very consistent. Strength in tasks needing that multi-step reasoning and knowledge manipulation, like MMLU Pro and BBH, it was seen across the board.
This naturally leads us to the fundamental question, then. Why? Why is this smaller looped model smarter? Is it simply that by reusing parameters, the model somehow packs in more raw knowledge, a bigger library, or is it fundamentally changing how it uses the knowledge it already has?
This is maybe the most counterintuitive finding of the whole deep dive, and it's one the researchers addressed head-on.
And what did they find?
The advantage is not in memory. Controlled experiments using a task called capo showed recurrence does not increase raw knowledge storage.
At all.
Not really. Both the looped and the non-looped models, they attained nearly the same capacity ratio, around 2 bits per parameter. The parameter count still dictates the raw storage capacity.
Wait, so it's not a bigger library, it's just a vastly superior librarian. How can the same amount of raw data stored in the same number of parameters suddenly solve dramatically harder problems? That goes against the core scaling hypothesis we've operated under for years.
That's the key insight. The superior performance stems entirely from enhanced knowledge manipulation capabilities. The parameters hold the atomic facts, but the recurrence allows for a much more flexible and iterative application of those facts.
How did they prove that?
They use synthetic tasks designed to isolate manipulation skills. For example, the mono task, which involves complex tree structures and modular arithmetic. It's basically a test of forcing the model to solve a complex multi-step puzzle.
And the looped models did better.
They consistently outperformed their non-looped counterparts with the same number of parameters, showing a better inductive bias towards flexible knowledge usage.
So it's not about finding the answer in a book, but about knowing how to perform the calculation using the information you've already memorized.
And they saw this confirmed in natural language tasks too, specifically multi-hop question answering. The looped models showed improved sample efficiency.
Meaning they learn faster.
They required far fewer examples to learn how to compose and manipulate atomic facts to answer multi-step questions. This really cements the conclusion. LoopLMs use the knowledge encoded in their parameters more flexibly and more efficiently because of that iterative self-correction.
Let's talk practicality for a moment. If this model is dynamically deciding how many computational steps it needs based on input difficulty, how does it manage that dynamic depth without becoming erratic in a real-world deployment?
That's where the adaptive computation mechanism really shines. They handled the depth allocation in 2 distinct training stages.
Okay, what's stage 1?
Stage 1, during pre-training, uses that entropy-regularized objective to teach the model a rough estimate of the depth it needs. Then, in stage 2, they fine-tune the learned exit gate by freezing the main model and introducing a specialized adaptive exit loss.
And what does that loss function do?
It's elegantly designed to minimize marginal improvement. Essentially, it tells the model, if an additional step is no longer giving you a substantial performance gain, exit now. It's an explicit cost-benefit analysis running internally.
That seems like a very resource-conscious way to allocate compute. Only spend the time if you know the performance is still improving. But there's always an elephant in the room with recurrent architectures. Leafy cache, right? If a model loops 4 times, you'd think you need to store the key value cache 4 times over, which would just obliterate any parameter efficiency gain you made.
That was the recognized challenge, yes. A naive 4-step recurrent model would indeed require 4x memory overhead for the cache. However, the critical deployment breakthrough was the finding on KV cache sharing during the auto-regressive decoding phase.
What did they discover?
They discovered that reusing only the KV cache from the last recurrent step yielded performance nearly identical to using the full memory-intensive cache.
So they maintained the performance benefits of that deep thought process while successfully achieving a 4x memory reduction.
That's the part that brings the memory footprint for LoopLMs back in line with standard transformers. It makes these highly efficient models genuinely viable for deployment. It's the key practical feature.
So finally, we should probably look at the implications for reasoning quality and safety. This touches back on that difference between latent reasoning and explicit chain of thought.
A really important distinction.
If chain of thought is often just a post hoc rationalization, writing down the steps after the model has already settled on an answer, Is the LoopLM's internal process genuinely a dynamic revision?
The evidence strongly suggests it is. They measured what they call causal coupling by analyzing step-by-step agreement on ambiguous tasks, like core question pairs.
And what did they see?
They found that the model was actively updating its decision as the recurrence deepened. For example, the answer given at step 2 only matched the final answer at step 4 in 36.1% of cases.
Less than half the time. That systematic disagreement across steps seems to confirm the model is genuinely changing its mind mid-process. The internal latent updates are real revisions, not just confirming a decision it already made.
It's not just confirming a pre-committed decision. And what's more, the architecture showed a unique property related to safety alignment.
Ah.
When they evaluated it on the XPHI dataset, the model's safety score improved significantly as the number of recurrent steps increased.
And this continued even beyond the train depth.
It did. The enhancement continued even when extrapolating beyond the maximum train depth of 4 steps. They tested it up to 8 steps, and it kept improving. This suggests that the latent thinking process itself refines the alignment.
That's fascinating.
Ultimately, this work firmly establishes iterative latent computation, or loop depth, as a crucial third scaling axis. It complements the size of the model and the volume of the training data.
So the immediate takeaway for you is this. Efficiency gains in LLMs are highly achievable, not just by increasing the brute force of the system, but by focusing on the substance how knowledge is processed, rather than just the scale how much knowledge is stored. This is a crucial resource-conscious path forward in model design.
It really opens up a new direction for research.
And this research touches on something profound about how knowledge is utilized. The theoretical analysis suggests that the recurrent architecture effectively provides the ability to perform a kind of search on the parametric knowledge graph, potentially solving complex graph search problems in logarithmic time. So a final thought for you to consider. How might this efficient latent search capability change the way we design algorithms that run inside the next generation of large language models?